Hi everyone, this is Karthik. I'm a data scientist at Kansai. Today I'm going to present our work titled Emergency Department Optimization and Load Prediction in Hospitals. This work was done in collaboration with all the people listed here who helped with from designing the solution, providing domain expertise, managing the project, helping with the research. Agenda for today is I'll go through introduction to the problem that we are trying to solve, and then go through all the steps in the life cycle of experimentation, where I'll go through formulation, data description, features that we used, ML models that we used to create these, train the model, and also evaluation metrics, custom metrics, and ML metrics that we used, and the results from these models, and briefly go over the real world deployment that we did, end-to-end system deployment, and also the future work that we plan to do. Coming to the introduction of the problem, ED is a major component of health system where based on the CDC study that was done in 2015-16, there are about 140 million ED visits in US and are growing rapidly. And the rate at which they are growing is outpacing the population growth, which you can imagine the impact that it will have on ED overcrowding, uh, as there are limited number of beds and EDs that are available. The major drivers of these overcrowding is the severity of the patients who are arriving in the ED, and the care, the number of patients who are receiving the care, or the ED census and ED arrivals. Is what is impacting ED overcrowding. As part of this work, we created this mental model, depiction of event mental model, where it shows what are the bottlenecks for in the patient journey in health system and in the ED. We identify various bottlenecks and the ML solutions that we can build to solve these to resolve the bottlenecks. The two problems that we are focusing on today is ED census prediction. Where we try to forecast the ED census for near future, and also predict the arrivals, number of patients who are going to arrive, the load prediction, and also acuity prediction as a way of prediction of arrivals in each of the acuity buckets. And there are three other solutions that we are working on, where we predict the risk of a patient coming back multiple times in a given time window, which is CEI laser prediction, and LWBS, which is risk of a patient leaving without being seen by a doctor, and also a patient at risk of being admitted to hospital. The high acute or severe patients who require long-term care are often result into being admitted into hospital. Coming to the formulation for the work that we are presenting today, we are trying to predict or forecast number of patients who are going to be in the ED and who are going to arrive in the ED based on their acuity buckets every 15 minutes. The reason we chose 15-minute interval prediction is the dynamic of the ED often changes pretty quickly, and we want to provide insights as close to real time as possible. And we ended up deciding on 15-minute interval predictions, where we predict every 15 minutes for next 2 hours, 4 hours, and 8 hours, where we forecast number of patients who are going to be in the ED and arriving in next 2, 4, and 8 hours. The rationale for the 2, 4, and 8 hours is 2 and 4 hours is short-term prediction, where if there is a surge in number of patients who are coming in or going to get treated in the ED, that will help the ED management to like ping or call in the on-call nurse to help with the overcrowding. And for 8 hours, they can plan for the next shift and schedule for more nurses if there is a surge prediction. And coming to the data, we worked with one of the health systems in suburban areas of Pacific Northwest. This ED sees about 60,000 or more ED visits annually. And the data that we used is from January 2014 to January 2018, which is 3 years of data, which we used for experimentation. In this data, we saw 206K ED encounters, out of which 199K had acuity assigned. And so we removed the encounters without acuity as part of data preparation. Uh, Normally, acuities are assigned based on ESI standards, where ESI is represented from 1 to 5, and 1 represents severe critical patients who requires care immediately, and 5 is less severe, who less critical patient who can be treated or wait for getting a treatment. So we observed that the distribution of these buckets is skewed, where we observe less number of encounters in less severe and more severe patients. So we bucket 1 and 2, which is more severe patients together, and less severe 4 and 5 together to get better representation and form 3 buckets. Coming to the features that we used in these models, we use prior census and arrivals of last 1 hour. At a prediction time point, we look at past 15 minutes, 30 minutes, 45, and 60 to get number of people in the ED and number of people arriving to the ED to just give us an idea of what will be the trend. And also we observed that census or arrivals it varies a lot based on the time of the day or month of the year or just quarter or those kind of time-based features. So time-based aspects. So we used these as features in the model, and also we use slope, which is to give just the indication of negative or positive trend. Coming to the ML models, we use, as we are predicting count, which is 0 to X varying number as a label. We use Poisson regression for GLM models, and also we used regularized penalties as part of GLM models. We also experimented with gradient boosting methods, the ensemble model. Coming to evaluation metrics, we used normal regression metrics, ML metrics, mean absolute error, and root mean squared error, which are typically used for regression models, and also to cater for the model, as this model is going to be deployed and used by the users, we created custom metrics. The problem that we are solving is to optimize the staffing in the ED. Typically, the health systems follow a ratio where they want 1 nurse for 4 ED patients. So we created a metric where we want to calculate the error being in between -4 to 4, and the percentage of times that the model is predicting in that range for all these models. That will give us an idea of how accurate we are and how helpful the model will be. Coming to the results, for census, we saw that gradient boosting methods have been are the best performing methods, and 2-hour forecast, which will help the ED plan for the near term surge, is the best model that we saw, and we are within 70%. We are within 4 absolute error for 70% of the times for 2-hour forecast, and 65 for 8 and 4 hour. Coming to the arrival predictions, the major bucket that we want to be optimized for is emergent, where we want to predict good for high acuity patients. We are within 4 absolute error for 96% of the times for emergent, and we also do good for urgent. Coming to the deployment, we deployed end-to-end streaming system where we were receiving data using SFTP from customer EMR, and SFTP, we had a service bus which was consuming the data from SFTP. And we had the models deployed as Docker service in Azure, which was listening to Azure service bus and consuming the data and creating features and generating the scores or predictions and storing in the DB. And we had a native UI dashboard which was showing these results. And also we had a monitoring framework where we were monitoring the uh, model performance over time. And this model was deployed for 6 months in a pilot, which was used actively by the ED management to make decisions. And we observed that the model predictions were within the ranges that we observed in training. The future work for this solution is to incorporate third-party data related to Google Trends, search trends, weather data, sports events, and similar. And also, we want to provide interpretability for the predictions that we are doing, and also incorporate concept drift framework to identify drifts in predictions and features. Thank you.